Hello everyone, good afternoon. I'm Ghasem Sharifi and today I present my achievement during the PhD work. The title of the PhD is Operational Solution and Validation of Critical Subsystem for Autonomous and Compact Deorbit Device Based on Bare Electrodynamic Tether, and my supervisor are Professor Gonzalo Sanchez and Andres Marcos. So to have an introduction about the tether, electrodynamic tether is a promising solution for deorbiting space debris, and ITPACF is a project in order to developing a flight-ready deorbit device using TRL-8 and basically include two modules that will separate from each other during the mission using the 420-meter line tether. And it's using the propellant Lorentz force that appear thanks to interaction between the magnetic field and current along the tether. So you can see here also the video how the system works, and also just as an example of the performance of the system for a satellite in 600 kilometers without any EDT system, it takes more than 10 years in order to deorbiting. However, if we use the EDT system, the duration of the deorbiting time decreasing to less than 70 days. So as you can see here, the satellite at the end will burn at the atmosphere. For the ITPACF project, both qualification campaign for the EQM and the flight model have been passed and successfully we reached the TRL-8. And the mission led by Perseus Space is expected to launch using the Vega C by Avio in 2027. Also in this picture, you can see some of the test campaign we did for both functional and environmental testing for the both shock, vibration, thermal vacuum, deployment mechanism system, just as an example of the test campaign that we performed for the validation of the project. So my contribution to this project was basically can divide it to 4 different things. The first one was for validation of ADCS attitude determination and control subsystem in order to characterize its components and verify the algorithm, the sensor selection, and the overall ADCS subsystem using the hardware in the loop testing. Also, another objective was characterizing the magnetic interference because the system is very compact. We are suffering from the magnetic interference, so it was very important to characterize its effect and propose some operational solution to mitigate that interference. Objective 3 was to propose some practical solution in order to triggering hollow cathode only in the proper time in order to preventing the wasting power that I presented in 2024. And the last objective was to designing the complete ground segment. That ground segment including the telecommunication subsystem, ground station, and all of the activity we should do after the launch of the satellite in order to monitor and uploading some command, health monitoring, orbit propagation, all of the activity that I presented, all of this activity last year. For the ADCS, we defined the project as to 4 main phases. After launching the satellite in orbit, satellite, because of the deploying from the launch vehicle, it has started to tumbling with a high angular velocity. The first objective is to reducing the angular velocity by the tumbling approach in the first phases. After reaching to a specific threshold, the satellite changing the phase to the pre-deployment phase in order to pointing the satellite toward a specific direction that's required for the deploying. After fulfilling this pointing accuracy, the satellite is starting to deployment. It takes 1 hour and 400 meter total will deploy. And after this 1 hour, we switch to the deorbiting phase. That in this phase, EDT system is working by generating the Lorentz force. At the end, the satellite burning in the atmosphere. So for the ADCS subsystem, we are using the bunch of sensors, using the different sensors as gyroscope, magnetometer, GPS, sun sensor, and as I mentioned, we are using 2 modules, and each module has a separate independent ADCS subsystem. For the attitude determination, we are using extended Kalman filter. For each phase also, we have different control strategy. For the actuator, for the first phase, we are using the magnetic torquer. However, during the deployment phase, we are using the cold gas in order to have much more authority of the control in order to tackle with the disturbance that we have in that phase. However, this system is very complex. There are lots of sensor actuator algorithm. It's very necessary to testing and validating the system on the ground before launching to the Earth. So we develop hardware in the loop testing, and for that first we state of the art with different setup that is possible to testing ADCS on the ground. However, by knowing the requirement that we need for ADC, that should be have a 3 degree of freedom of rotation, less magnetic interference, low friction, and also compatible with the size and mass of the package project, we finally selected rotational air bearing setup. And by selecting that, we fabricate and design a nanosatellite simulator that can compatible with up to 6U satellite, and also we design the mass balancing system in order to remove the gravity gradient. For the simulating the sun, also the sun simulator, also in order to replicate the eclipse and illumination time of the satellite during the orbit, was designed, and also Earth albedo simulation in order to replicate the reflection of the light coming from the Earth on the satellite. So you can see here in the left all of the integration of the setup, and also in the right how the system is dynamically rotating and performing as an example. So by using this setup, now we were able to testing ADCS subsystem to testing different functionality of them. For example, for the testing the sun vector estimation using the bunch of photodiode installed inside of the satellite, for estimating and also validating the EKF algorithm we developed by comparing the reliable reference sensor, and also the end-to-end test that by using all of the real sensor of the satellite algorithm embedded on the processor of the satellite. So we, with this end-to-end, we validate entire of the subsystem of the ADCS. So you can see also some of the results. We test attitude determination both with the main sensor and also with the backup sensor to be sure that even if we have some failure for the satellite, the backup sensor can also fulfill our requirement. Also, you can see some tests. We did tests also for both sunlight and eclipse condition. And in all of the tests, because the attitude accuracy that we need was less than 5 degree error, with all of this condition, also in the worst case that we are using all of them for the backup sensor, the accuracy, the error is less than 2 degree. Going to the second objective was the magnetic interference. Because the system is very compact, we are suffering from the magnetic interference, and what's very important to know to characterize the level of the magnetic interference that we have. And it can be divided to magnetic interference on the control and also on the measurement and attitude determination. For the control, because we are using, inside of the satellite, there is a lot of electrical component, wiring, ferromagnetic material. All of these things, they are generating a dipole. And this dipole, when the satellite is in the orbit, by interaction of the magnetic field generated disturbance torque. So it was very important to characterize, to knowing the level of this disturbance torque, and to knowing the magnetic actuator that we have can tackle with this amount of disturbance or not. And also, we have two main sources of the interference from the cold gas system and from the deployment mechanism. That was very important to know how much is the effect of these two sources of interference. For residual magnetic dipole, we need a setup to knowing the dipole position, dipole direction, and also the location of that. So first, we develop a specific software to measuring the magnetic interference, and also we did a sensitivity analysis to knowing what is the effect of the room noise of the magnetic field on the measurement, also to knowing how many sensors we need to have a good accuracy for the dipole estimation. We did a CAD design, the manufacturing, integration, calibration of the sensors. Also, we validate system by using the noun dipole generator system. And finally, also we benchmarking system with another setup to knowing what is the level of accuracy comparing with another setup that is typically using for this residual magnetic dipole estimation. And finally, for each phase of the satellite, because in each phase we are using the different combination of sensors and actuator, so for each phase we have different level of the magnetic dipole. So for each 7 phase that we have, we characterize and we estimate all of the dipole parameters. Another source of the magnetic interference was from the cold gas system. Cold gas system using the valve. For each module we have 4 valve, and the valve acting like a solenoid, and when we have a current, this current generates a magnetic field. So what for us is very important that where we should put our magnetometer, that interference very less from this effect of magnetic interference. So we use the setup that we develop for the residual magnetic dipole. We put the valve inside this, and after that we characterize the dipole direction and the magnitude. And by knowing that, we, as you can see here, we define where is the position of the magnetometer should be there in a satellite to get less interference. However, also another source was the deployment mechanism. We are using the servo motor for deploying the system. Servo is using some permanent magnet, and by rotating, they are generating the magnetic field. So the effect based on the velocity profile of the deployment mechanism can characterize, and the error was so high, and we make a very tough decision to, in that phase, when the motor is working, we are not using the magnetometer for the attitude determination. So as a conclusion, we validate both ADCS, also characterized by magnetic interference, and by knowing all of this result that we get, we did several design revision for the system for both ground-based in-orbit procedure, algorithm revision, and also onboard logic procedure. So achievement that I had some, basically 2 journal papers, attending to some conference, and also going to research visit to Denmark. And finally, achievement is the technology transfer and commercialization. So 2 products that we developed for the validation of the setup now is transferred to the market, and now product available through the Perseus space. So thank you so much for attention. If you have any questions.